In this video, we're going to talk about sequences, and this is section 11.1. So a sequence is defined as a function, a sub n. So the notation will either use these curly brackets, or sometimes we'll just list them out, a1, a2, a3, a4, so on and so forth. The reason we have these subscripts is that a sequence is a function from the natural numbers to the real numbers. So it's a list of terms of real numbers, and there's one for every natural number. Natural numbers are the numbers, typically we start with 1, but we can also start with 0, n equals 1, 2, 3, so on and so forth, all our counting numbers. And the only thing that needs to happen is that each of these terms is a real number. And you can talk about the first, second, third, etc. terms in the sequence. Another notation we sometimes use is the a sub n, n equals 1 to infinity, to sort of overemphasize that it's an infinite sequence. And sometimes we'll put those curly brackets around this list. So here's some examples of sequences. The first example is a very famous sequence that you may have heard of. 1, 3, 6, 10, 15, 21. Look at this sequence. How do you think I made each of the terms? Notice our first term is 1. Our second term is 3. To get from 1 to 3, I added 2. Our next term, a3, was 6. To get from 3 to 6, I added 3. So 6 is really equal to 1 plus 2 plus 3. The next term was 10, and notice to get to 10, I added 4. So this is the sum of 1, 2, 3, and 4. So on and so forth. So 15 represents the sum of the first 5 numbers, 21 is the sum of the first 6 numbers, and so on forever. So the nth term in this sequence will be 1 plus 2 plus 3 plus every natural number up until n. And this sequence is often called the triangular numbers. And it gets that name because you can create triangles like this. Each row of the triangle has one more item in it, and those represent the total number of dots in the triangle that represents a particular triangular number. So here I've represented a4, for instance. We can see that a4 is 10. So that's one example of a sequence. Let's look at another example. Another example playing off of that might be familiar to you is the following sequence. 1, 1/2, 1/4, 1/8, 1/16, 1/32, so on and so forth. What do we think is going on here? Well, you'll notice that if a1 is 1, then the next term, a2, is 1 times 1/2. a3 represents 1/2 times 1/2. a4 represents 1/4 times 1/2. So every single time we're multiplying by 1/2. When there's a constant ratio that determines the next term like this is an example of a geometric sequence. The general form for a geometric sequence is that a sub n will equal some initial value a times r to the n, where r is a constant ratio. Every term just then is a greater power of that number r. So in our example, this is the sequence 1 times well, actually the way I have it, it's the way I drew the geometric sequence here, it's really a times r to the n minus 1. 1 half to the n minus 1, where n goes from 1 to infinity. That would represent the particular sequence I've listed here. So that's a second example of a sequence. Let's do another one. So this next example, we could consider this sequence. This is the sequence that always gives the value 1. So it's a constant sequence. Another example is a famous sequence is this one: 1, 1, 2, 3, 5, 8, 13, 21. This is the famous Fibonacci sequence. The Fibonacci numbers are a famous example of a recursive sequence. So the way we typically describe the Fibonacci sequence is to say that the first term is 1, the second term is also 1, and then to get the next term, whatever term n plus 1 is, we add the previous 2. This is an example of a recursive definition for a sequence. So recursively defined sequence. We can't describe the nth term directly, so instead we describe that sequence by how you get from one term to the next. Let's look at some more. Let's do one last one. This is an example of an arithmetic sequence. An arithmetic sequence might be something like this: 1, 3, 5, 7, 9, 11. Now that sequence maybe is better known to you as the sequence of all odd numbers. What makes it arithmetic is that every term is obtained by adding a constant to the previous. So 1, 1 plus 2, 1 plus 2 plus 2, so on and so forth, which means as a recursive definition, we can define this as the sequence where a1 is 1, and then the nth term of the sequence is the previous term plus 2. So from this definition we can see that a2 would be a1 plus 2, or 1 plus 2, which is 3. And now that we know what a2 is, we can figure out what a3 is. a3 is 3 plus 2, or 5, and so on and so forth. Now you'll notice in most of the examples I've shown here, we have sequences where the values keep getting bigger as n grows. So that was the case with this arithmetic sequence. The numbers keep getting larger, as well as with the Fibonacci sequence. But in the case of the constant sequence, and then also in the case of this geometric sequence, that's not the case. So in the constant sequence, every term appears to be 1. So if you were to see what the trend of the sequence is doing as n gets infinitely large, you'd expect to have the answer that there's a notion of 1. The sequence can have limits, and the limit of this constant sequence should be 1. The geometric sequence, well, in my example that I had here, 1 times 1 half to the n minus 1, as n gets larger, that's going to shrink. So we'd expect as n tends to infinity to have terms of this sequence go to 0. In the last example, the triangular numbers, we again had an example where the terms were growing infinitely large. So already from this, one thing we can think about is classifying sequences as to whether or not they converge. whether or not there's a limit, and so we'll do that in the next video.